the poster prize for this session. It's just there. Yes. So, Agustina.
The winner.
So thanks all of you. Actually, I wanted to comment on that. I think the poster sessions have been great. I've seen a lot of you discussing a lot of the papers, and I've seen a lot of effort on doing and explaining your work. And I think that's really great, and I think that worked out well. So thank you for that, and I hope it leads to a lot of interactions and collaborations, which is kind of part of the whole point. Okay. And so for the final Tarek lecture, when we actually know if it's measurable or not, if the order parameter of the glass is there or not. Yeah.
Suspense.
Okay, Tarek, all yours.
It's okay? I'm not exactly sure what is okay and what's not okay. Okay, it's been a while. Hi again. So this is a final lecture. It's the final countdown. So last time I left you on a cliffhanger, you know, classic end of the episode type thing, where we were discussing analytically continuing these equations to real time. So we mentioned, okay, so let me recap. So in Euclidean time, imaginary time, our spins at each lattice site are functions of this imaginary time tau. And they're equal to their periodic functions in the inverse temperature. And the effective theory that we derived was a theory of this replica matrix QAB of tau prime. So when we added dynamics to the system, then our replica matrix now obtained a time dependence. And this changed the story only slightly. So we still had non-trivial structure of overlaps along the off diagonals, which were time independent. And what we found was also that instead of having one along the diagonals by the spherical constraint, this got replaced by a general two-point function, q of tau prime. And the spherical constraint was visible from the fact that q of tau comma tau, which is the same as q of 0, is equal to 1. So the correlation function has to start at 1 and then decay. And I didn't show you this, but I told you this. The equations satisfied by this q of tau prime in the off diagonal exhibited this kind of split behavior. So for temperatures above the spin glass transition, it looked like this. This is tau over beta equals 1. This is 0. And so green is T greater than TC. And if you crank the temperature down, what happened instead was something like this. This is T less than TC. And we left it as a question. I guess yellow and green are not very distinguishable. Is blue better? No. So this function is bounded from below by the quantity u, which you can solve for using static equations. But of course, so this is nice. This tells us something, something nice. We don't need to replicate our system in order to see this quantity u, this special order parameter for the glass transition in this model. We just need to be able to perturb our system and see if it relaxes back to the original state or if it goes to some nearby state as measured by this bottom of this expectation value. But this requires us to be able to do the experiment in imaginary time, which we cannot do. We have to be able to do the experiment in real time. So I went through this very long derivation just so that you can see all of the things that you have to think about when you're trying to study these systems at finite temperature, but nevertheless in real time, of how we analytically continue the equation satisfied by these Qs into the real-time domain. We developed all sorts of tricks, which you can check in your notes to see. I'm not going to rederive that because it was very long and tough. But yeah, so then we wrote down, so just one, I want to remind you, we wrote down one final equation for this thing called, I called it QR retarded of real time. And QR retarded of real time is, so it was something like theta of t q r bigger t minus q r. Let's see, let me get it right. Yeah. And this QR of tau was defined, so this is in imaginary time, now remember. You guys can see the difference between t's and tau's? Okay? Yeah, so this QR of tau was defined as q of tau minus u. So this QR goes to 0, so you shift it down. So instead of starting at 1, it starts at 1 minus u. And it goes all the way down, like that, but it doesn't go back to 1. And I asked you to think at the end of last class whether if we measure this guy, we will be able to see this parameter u in it or not. So who thinks that you'll be able to see it? I see one hand, 2 hands. Who thinks you won't be able to see it? Guys, voting is mandatory in Brazil. No, you have to pick. You have to choose what. There's no I don't know option. All right, who thinks that you're going to be able to see it? Okay, that's a bit better. Around a third of you. Who thinks you won't be able to see it? let's do it again. Who thinks you're going to be able to see the U dependence? Okay, who thinks you won't be able to do it? To see it? Okay, seems like 50-50. The suspense is killing me. All right, so now in experiments, the only thing that we can measure are these retarded correlation functions. So now, do you guys want me to review what this greater and less function is? So we called Q of t greater. It was let me get my definition out. Where did I write it? Sorry for the delay. Give me a moment. I need to find it. Ah, yeah, here we go. Where epsilon is greater than 0, and q less of t was q of tau equals minus it plus epsilon. So this Euclidean correlation function of QR will start at 1 minus u. What about the retarded correlator for QR? Where do you think it'll start? Somebody needs to say something. At t equals 0? Zero, very good. Starts at 0. So if we plot these functions, so yeah, so I want to show you the phase diagram again. So this is t over j. This is 1 over mj. And remember, in this direction, we're more static. Remember, because a bigger m meant bigger cost to wiggling. So, and we had this kind of phase diagram. So here we had spin glass. Here we had disordered. And this was the transition line. So now let me show you what happens in the spin glass phase, but for mj, for mj small, which means it can wiggle a lot, you get a function that looks like this. With some profile like this. And what happens as you tune mj to be bigger, you get now I'm going to use yellow because we're all so green. Remember, green was I used the bad bad color. So hold on, no, that's fine. We're gonna just change the color. So this is MJ small. And we're gonna use orange for MJ big. So MJ big, what happens is that this thing wiggles like maybe once and then decays. And this is both in the spin glass phase. And if you go out here, if you go take the temperature above the spin glass transition, let me show you some plots. So this is so what does it look like to you? Is it possible to tell the difference? Huh? The zero, what do you mean? Oh, sorry, I didn't mean that. That was an accident. They look kind of similar, right? Okay, so it's not something that you can obviously see from the plot. Okay, so now I want to take another vote. How many people think you can see it, the U from these plots? Raise your hand if you think yes. How many people think no? Okay, so no has, now you've updated your priors, no has a much bigger backing. Okay, so what's the answer? This is a nice controlled experiment in democracy. I kind of like it. Okay, now I want to remind you of something that I mentioned before. Remember that at the end of last class, we derived this equation for a general function of tau. We had the integral from minus infinity to infinity and I also mentioned that the retarded correlation function as a function of omega, you could write as the integral of d omega prime over 2 pi rho of omega prime divided by omega plus omega prime plus I epsilon. Okay. So now let's imagine plugging in here. So now let's do this for this QR of tau. So QR of tau we have is equal to minus infinity to infinity of d omega over 2 pi e to the minus omega tau divided by 1 minus this Boltzmann factor, rho, and then sigma sigma of omega. And the whole point of solving the real-time equations, if you go through the derivation, you need to, as an intermediate step, find the density of states. So you're going to have some very complicated set of equations, and the only way to solve for the real-time behavior will be to turn it into an equation for this density of states, right? And now I want to remind you of this and this definition. So if I plug in tau is equal to 0 here, then I get 1 minus u is equal to the integral over all frequencies, or 2 pi, integral of rho of omega over 1 minus e to the minus beta omega. And this rho is the same rho as the one that goes into the retarded correlation function. So it's not something that's super obvious from the plots, but it's something that is some global feature of the density of states. So it's not a very obvious thing that you can read off from your plots, but if you have very good control, then potentially you can measure this object. So take that as a defense of democracy. We still have to have opinions, even though we don't have the full information. So the upshot is, it's very difficult. It's very difficult. But in this model, it seems like it's something that you could potentially measure if you have very good control. Now, of course, one has to now come up with a setup where the effective physics is reasonably captured by this kind of p-spin model. And well, that's a question more tuned for our experimentalist friends. But this is the raging debate in the spin glass world. So spin glass people say we have identified an order parameter. It's measurable, albeit very difficult to measure. Here's how we do it. Now go and find it. And experimentalists say, well, I can't do these experiments. This is not a reasonable thing to ask me to go measure. So it seems like, there are two camps. People think the glass transition is defined. People think it's not. And maybe you'll find it interesting to try to come up with something more sharp than this kind of very subtle experimental observable. Okay. So so with that, I basically have said all of the things that I wanted to teach you about this example of a statistical system that's out of equilibrium. So as a recap, what we did was we solved this kind of complicated model. It has a lot of disorder. We know it has a glass transition. And then we went through all the procedures necessary to analyze this model in complete and gory detail. Statics, dynamics, everything that you want. And in the end, we we ended with a little bit of a bust. Our experimental order parameter that we want to characterize the system with, something that's very hard to measure. So now I guess I just want to ask, so there are many reasons why this stuff is interesting to theoretical physicists. One is, are there any holographic applications? To these techniques? Two, cosmological applications. And three, particle physics. And so I'm opening the floor. You can ask me about these kind of applications, and if you have any interest, I can maybe discuss some of them. No, you have to tell me what you want to hear about.
Holographic applications.
All right, this is democracy.
Please. Pretty please.
No, I agree. I just want to ask a question before you go into the topics. So, having identified this order parameter, where it's measurable or not, and having in mind that there are other places in physics where replicas play a role, is there any intuition why looking at replicas would be a good idea for a classy system? Or why does it show up when you do that by hand?
Replicas are the natural thing to consider when you want to compute a thermodynamic object with disorder. It's just, if you have a flat distribution over your couplings, and you want to compute the log of something first, and then integrate over the couplings, the only reasonable way that we have to do that is to introduce replicas by hand, and then hope that we can continue.
But is it just a mathematical trick?
It's a mathematical trick. It's the
is
same
there an
as
interpretation to that?
when you try to compute entanglement entropy by first introducing Renyies, right? You replicate your system n times, you try to understand the analytic structure as a function of n, and then take n to 0. It's the same. Logs are, whenever you have a log, replicas seem to be a natural thing to introduce.
That being said, I do agree with the holographic applications.
Can I make a comment on your answer? On Renyi entropies, for example, suppose you have a Gaussian distribution and you do a Renyi entropy of that. You can, suppose you know all of the Renyi entropies, you can recover how tall are your bars, but you do not recover the order. So you don't know. You can think of it as a transform, like a Fourier transform, but of different sort, that contains a little bit of information. Well, contains some piece of information, but not all the information of the theory. So that perhaps can give you a more intuition on why do you do that. It's a transform that loses some of the information. You don't know if you have a Gaussian or the bars dispersed there, but you know that the tall. How tall were there?
I want to know what the students want to hear about. That's what I have some organizers' opinions, but what about the students? You can just blurt it out.
I actually have a question about holographic applications, so prefer to start, and then I ask the question.
I would like cosmological applications because mainly because in holography we learn that normally theories are dual to a CFT, but here we saw that the replica trick is useful when you want to compute something that involves an average over theories, and since in holography you have only one theory, then that seems to be not the right place to apply it. So.
Okay. So who wants holography? Who wants cosmology? Holography, raise your hand. No, you can't raise two hands. Okay, and cosmology? Okay, there's a clear ordering. Okay. Well, we'll see where we get. I don't know. This is complete ad-libbing right now at this stage. I don't have anything prepared, so. Okay, but obviously before I get to the holographic applications, I'll leave this up. We'll maybe discuss all of them. Are there any questions about just what we did over these last few days that might still be confusing, or that you want any clarification on before we kind of go off topic? It was all crystal clear. Everybody understood everything about spin glasses now. You know how to solve every model you may encounter. Sorry? Clear as a glass. Glass clear. Wow. Some glasses are not very clear, you know. like what's the type of glass that's in a church? These, yeah, that stuff. It's kind of opaque. Stained glass. That's the one I was looking at in English. Okay, so holographic application, I can think of a few actually. Actually, one of the things that led Dio and I and Frederick Denef many years ago to start learning about these kinds of systems was this very intriguing phase transition that happens in black holes, in flat space. So in 4D flat space, you can imagine the following thing happen. So at large distances, we can just think about Einstein and Maxwell together. And the solutions to Einstein-Maxwell theory are charged black holes, right? And one of the first examples of a of a black hole with a non-trivial causal structure is the Reissner-Nordstrom black hole. And this is a black hole. It has mass m and charge q. And these black holes have a temperature, which is a function of m and q. And of course, I didn't prepare any of these formulas. As you know, there is a function where m becomes a function of q, for which the temperature equals 0. This is called the extremal black hole. So this is the extremal black hole. And as you also know, these extremal black holes have, they develop a piece of their geometry that looks like ADS2 in the near horizon region. So if I just sketch this geometry, so this is just a spatial slice, R3, and then there is a region, draw it in red, where the black hole becomes infinitely redshifted away. So it takes an infinite amount of proper time to fall into this black hole. And this is in the extremal limit. And actually, I can write my metric like this. And this function h is just a function of the 3 spatial coordinates. And if I plug this into the Einstein's equations and the Maxwell equations, then I find that the only thing that h needs to satisfy is box of h is equal to 0 away from the sources. Which means that h I can write as 1 plus q over x. So this is for the extremal black hole. But here's an interesting other fact, is that I can also solve this equation as follows. H is equal to 1 plus q1 divided by x minus x1 plus q2 divided by x minus x2, where q1 plus q2 is equal to q. That's another solution of this equation with the same mass and the same charge. So this solution looks like this. Here's a spatial slice. At some point, there's a throat. The throat gets very deep, but then the throat splits into 2. So there's Q1 in here, Q2 in here, and there's a Q in here. So from very far away, it's very difficult to tell between these 2 geometries. It's very subtle which one you're in. All right, so I want to see some votes. Who do you guys think is the dominant solution from a free energy point of view? This one, more symmetric? What about this one? No? Nobody thinks this is the dominant one? No? I want to see some hands. Who thinks this one's the dominant one? Who thinks this one's the dominant one? Temperature is 0. It's this one. There's actually a tunneling amplitude that takes you from this one to this one. It was discovered by Brill. And this instability from a single black hole to split into 2 is called the fragmentation instability. And, okay, so now let's put our holography hats on.
What's the interpretation to have two charges in the other solution?
What's the interpretation?
Yeah, I don't get it.
It's just
What is Q1 and Q2?
Q1 and Q2 are arbitrary, that so long as they sum to Q. I'm just saying that, say I'm telling you I want to solve Einstein's equations at fixed mass and charge, M and Q. There are a bunch of solutions. One is one with one black hole, and the other is one with two black holes where the charge is split. And in fact, you can split it as many times as you want. There's nothing that stops you from even splitting this Q1 into 2 and this Q2 into 2.
There are two black holes in
Here there are two black holes.
in the same region of the space.
Well, no, you see, this is X1 is the event horizon of black hole 1, and X2 is the event horizon of black hole 2.
Okay.
They're separated.
Thank you.
Wait for the mic, please.
The Ricci scalar is going to diverge, but where?
The Ricci scalar diverges.
You have a singularity, right?
Yeah,
Maybe
at the origin. Yeah, so these coordinates don't cover the interior of the black hole.
Okay.
You have to extend the coordinate. This is just these are just good coordinates outside of the black hole.
But it would be like in no. But if you extend it, you would have like main points where the Ricci scalar
Yes.
diverges. Okay,
Yes.
thank you.
Yes. You have multiple singularities in the space.
Are you claiming that the three charges is subleading with respect to the one with two charges?
No.
Ah.
No.
Thanks.
What stops you from distributing the charge in all space if you can separate in two?
Nothing. I'm just trying to make clear, and I think everybody is getting it, that this scenario is very unstable. So it's not super dire. The time scales involved are very large because the process for going from that state to this state is a tunneling event. So if you have a very big black hole, you can imagine that the tunneling action to go from this to this is very, 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 very big. So it's not easy to go from this state to this state. Nevertheless, the system wants to go here. The tunneling probability is very small. So it's not like if you produced a single very low temperature charged black hole, it'll want to split immediately. It's pretty long-lived.
It's still true, but at small but non-zero temperatures?
I imagine so. Yes, I mean, no one has shown it, but of course the intuition is that that should be the case, yeah. Yeah, that's true. That's a good point. So the reason why these two solutions are both solutions to the equations of motion is that you see these positions are not set by anything, and really what you have is you have a system where the gravitational interaction, the Coulomb force of gravity, and the Coulomb repulsion of electromagnetism are exactly canceling. So at small but finite temperature, you have a mismatch. And so things will want to collapse into one. So then there's a difference between the... So one is clearly favored over the other. That's what Dio's saying. Wait for the mic, please.
So the question is related to what he asked. Does it split like in two black holes or into one black hole with two throats?
This is two black holes. The two throats is two black holes.
Okay, but no, it's mainly because because of the drawing, I was thinking there was only one event horizon, but I mean there are two event horizons. You said, right?
Yeah, there are two event horizons. Yeah. It's just that what kicks in as the throat, like you have to define what you call the beginning of the throat. There's no, that's an arbitrary thing that you set. Yes, you can escape this.
Okay.
This is not an event horizon. Okay, so this is fragmentation instability, and there are many ways of souping it up. So, for example, in string theory, so in compactifications of string theory, these things can be made much more robust. So there are extra scalars that come from compactifying that add extra forces, and in fact, in supersymmetric theories, these x1 and x2 are actually rigid. They're not something that you can move around because there's exact cancellation. There's some kind of configuration that's stuck. So when we were learning about these spin glasses, we were thinking, okay, maybe one way to describe this instability. So this is something that we never discuss in holography, right? This is something that has been known since the 90s. This is a paper. This fragmentation paper is a paper of Michelson. I guess Maldacena is first.
That color is a bit hard to see.
Okay. And Strominger. So this has been known, I think, since 1998. And of course, if we have some holographic description of a ADS2 black hole, like SYK or something like that, then somehow there should be a mechanism to describe this transition. And I think to date, there's nothing sharp that's ever been made precise about how to describe this transition. And we tried for a while to make a claim that this transition, this fragmentation transition is related to this idea of wanting to disorder. At low temperatures, you may have some complicated free energy landscape, and so you're entering something that looks akin to a spin glass phase. But as I was mentioning throughout this course, the order parameter to see that transition is very hard to measure. So it's very hard to make a clear statement about how you relate this to a spin glass phase.
Hi. Sorry that I'm not clear on something. The fragmentation is only like on two throats, or you can like continue?
You can continue. Yeah, this question was asked a little bit earlier. You can keep going. It'll make a mess.
Intense. Sorry. Thank you.
Yeah, so if you find this exciting, if you want to keep solving spin glass models, maybe one of you will be clever enough to be able to find a sharp indicator in these geometries as to why it should be described by something like a spin glass. Or maybe it's not a spin glass. Maybe we're barking up the wrong tree.
Sorry. Why are we seeing a extrema black hole without temperature when we study spin glass with temperature? And I remember that spin glass transition without temperature have a problem. So I will expect
At zero temperature.
Yeah, maybe it was many classes ago. But
No, here. So for example, here, I showed you a phase diagram, right?
Mm-hmm.
So here, the zero temperature is this line, and there is a spin glass transition.
Yeah.
So it's okay. You can still have a spin glass transition at zero temperature.
But we saw that was stable or something like that. That we Oh, maybe I'm confusing. Yeah, I should check, but I think I'm confusing when we try to put the temperature without the U. I think I'm confusing with.
Yeah, the replica symmetry phase.
Yeah, I think.
Yeah, there was one part in the analysis where we studied the replica symmetric solution, and we found that this was not the correct free energy minimum.
Okay, thank you.
Why you need extremality?
Why do I need extremality?
Yeah.
Well, this is just in this case, all of these solutions are known at extremality. But this fragmentation instability was studied at extremality.
No, yeah. Why the fragmentation needs extremality?
Why does it need extremality?
Yeah.
It's precisely this. So, in Einstein-Maxwell, it's precisely this fact that if you want to have, the existence of this geometry comes from the fact that the mass, the attraction from gravity cancels the repulsion from electromagnetism. If you weren't at extremality, one would win over the other. The gravitational attraction wins.
Okay.
Do you also have a picture here of you land there or there if you sort of cool it too fast?
Yeah, now you can you can imagine exactly. Yeah, so this was exactly the type of scenario that we were envisioning. So when we studied this problem, we were thinking about this example in string theory where you can't freely set the positions of these charges, and so you can imagine heating up the system a little bit, and the system at finite temperatures will still have this like fragmented structure. And yeah, we were imagining the following: you start at high temperatures. This thing is a single blob at very high temperatures, and then you try to like rapidly cool it and see where it ends up. And yeah, there it might start spitting things out in a very different way. Maybe it doesn't spit everything out. And if you, of course, took that system, heated it up, and then cooled it again, it'll end up in a different configuration. So we were imagining that this was like, perhaps, we were like in the right direction. But again, on the gravity side, finding the right order parameter is really hard. It's a lot like trying to understand how to read these plots.
It's in order to have stability in this second
Stability?
You say that this solution is more stability than the first one.
Well, this solution has higher entropy than this one.
But in words of stability?
Well, there's thermodynamic stability is the
Okay,
thing.
my question is...
one has lower free energy.
In that fragmentation, you need to have two equal copies of the same black hole with the same mass?
No. You split the mass arbitrarily, Q1 and Q2, so long as they sum up to the original mass.
I think that solution is not stable if you have two black holes with different masses.
I mean, okay.
In a long time,
plug this into Einstein's equations. And Maxwell's equations, and you'll see that the only thing that you need to satisfy is this. So these are two just equal solutions, and they have the same total charge. If Q1 and Q2 is equal to Q.
Okay.
Okay. So that's...
sorry, a little question. This is just something for planar black holes, or
No. These are spherical black holes.
Okay. Since you write X vector, I confuse.
Yeah, but these are spherical black holes.
Okay.
It might not look like it. In this coordinate system, the black hole horizon is at x equals 0, but it has a finite area. It's just a simplifying coordinate system, but you can, of course, you can write the Riesner-Nordström in polar coordinates or spherical coordinates, and it's the same solution. So that's holography part 1. But how much time do I have? Like 45 minutes? 20 minutes? 2 hours? Okay, so the next thing I'm going to say is very speculative. Let me erase all of this. Okay, so I mentioned this briefly in the beginning, but of course something that's very interesting, an interesting development over the last few years is this island formula. And let's think a little bit about what this island formula is, right? So you're trying to compute the entanglement entropy or of a system, of your quantum field theory. And what we do is first, so we want to compute SEE, which is minus trace of rho log of rho. But we can't do that. It involves a log. Logs are hard. So instead, we first compute the Renyi entropy, which is trace of rho to the n. And you can see that these are related by, so let's say, call this n, d by dn of Sn, limit as n goes to 1, and I think I have to have a minus sign. So very much like what we did to compute the log of the partition function over disorder, when you want to compute entanglement entropies, you're also instructed to replicate your system n times and then continue the number of replicas, in this case to 1. So the upshot of the island formula is, okay, people draw these pictures. So this is copy 1, this is copy 2, this is copy 3. And what people draw is they say, okay, at early times, I have something that's where each geometry is connected, has its own semi-classical description when I'm computing the entanglement entropy of the system. And the problem with computing the path integral, and the reason why I got the page curve calculation wrong all these years, was because at late times, this is not the correct saddle. At late, so this is early times. And early times, we could maybe call replica symmetric. And at late times, what people showed was actually the correct geometry to consider in the replicated space is one where everything is connected. and they drew these octopus diagrams. And this is also replica symmetric. And this is, yeah, so this is early times, this is late times. And this is the transition from this configuration to this configuration is what people attribute to this thing called the page curve. That's what gives the S entanglement entropy, this early growth, and then the decay. Now, in this setup, you know, this is a big success. We're always staying in replica symmetric configurations, but, you know, physics can be kind of wild, and it would be interesting to explore situations where the dominant saddle is not replica symmetric. It may happen in certain cases. It may be even related to this fragmentation instability that I was describing before. So I think it would be a nice thing to explore whether or not you can get replica symmetry breaking in these setups. And ask how that might be diagnosed. Remember, we started this whole course by describing the fact that any physical system that you may have interest in, that you can build in a lab, will have a glass transition if you cool it quickly enough. And why would gravity be any different? You know, maybe you start with a black hole, it's very hot, you try to let it equilibrate, and then all of a sudden you cool it very fast. Maybe all of a sudden you break replica symmetry or something like that. It should be something that happens, and if we're going to claim to understand black holes, then perhaps we should study something like this. Okay, are there any questions about that? Shall I move on to cosmology? No. Why not? Draw another black hole, okay. Shall I just end it? We can all go to lunch early, 10 minutes early. All the interiors. Supposedly. That's the page curve. That's the page curve. Yeah, so thinking about replicas is actually useful in the sense that here's an example. It's a 50-year-old problem, and it wasn't considered solved, in quotes, until people thought about replicas in a deep way. There's a bit.
Normally, one says that the replica symmetry is a fact that you have. It's an aspect of the saddle point because of the Einstein equations. And here you said that if you cool the black hole fast enough, there might be saddle points that are not replica symmetric. You're implying.
Very, very speculative.
Okay.
I'm not making any claims.
Okay, and the cooling should be interpreted in the other direction, the heating in the late times of.
I don't have anything very specific in mind, so you can fill in the blanks however you want.
Okay.
You can be creative. You should be creative. Let your research drive take you wherever you want.
Okay.
Tarek, the solution we found, or at least I think in my interpretation of this, that you showed us that in your system, this replica symmetric solution was not the dominating one, and
Yeah, in the spin glass,
in the spin glass,
case,
yeah, in the
it's
spin
not
glass model.
dominating. That's correct.
That's not dominating, and the one that is dominating in the end. Okay, but I don't know about the one that is dominating, but for m equal 2 would be something like that. It connects one with the other and one with the other one, but not between those.
Correct,
They are
yeah.
connected to
Yeah,
pairs or
yeah,
something like that.
potentially. Potentially there's some picture like this where you have some collection that are connected and some collection that are just not connected. You just bunch them.
Very good, thanks.
So there were 2 people who raised their hands for the cosmology. I should really let
minorities are important in democracy. So.
No. We should always, make everybody happy. I really should let Dio tell this part of the story because he, I think, wrote the only paper on this subject. Yes? Has anybody else written a paper on this subject? And Schenker and Suskind and Douglas Stanford. Okay, so Dio isn't the only one. He's the only one for me. As if the world doesn't know. Okay. Cosmology. So, well, you heard in Guy's lectures and in Dio's lectures that we would like to understand expanding universes. So we start from some system, very fine-tuned initial conditions, and then all of a sudden, the state of the early universe, if we look at the history, the state of the universe inflates, and what happens is that you start with some quantum state, psi, and under time evolution, different patches of the universe fall out of causal contact from each other and freeze. And this is something that you heard over Guy's lectures, right? The equations are oscillatory when they're very squeezed, and then at a large separation, they become exponentially damped. And so what happens is that you have some very quantum state over here, and over here, you can break up your universe into different patches that are out of causal contact from each other and classically frozen. And an interesting question is to try to come up with, so of course, what the study of inflation is to study the quantum dynamics of this entire history of the universe, right? And to understand how it imprints on the CMB fluctuations. But another approach to this would be to try and come up with an effective set of classical dynamics that describes the probability distribution of the state in these different patches. You can ask like some theory for the probability distribution of the state Q in these patches, and I'm gonna write it as follows: Q minus Q alpha beta, where Q alpha beta is the overlap between uh, alpha and beta. So you can ask, is there some maybe stochastic evolution that gives us this probability density, and how should we think about it? And if you actually study this probability density, you'll notice a very interesting structure to it. These overlaps tend to not live on some continuous space. So these Q alpha betas don't take values over the real numbers, but they actually take values in something that looks like a tree. So for example, you can ask, say this is alpha and this is beta. Their distance, Q alpha beta, you would count one, how many rows up the tree do I need to go until I match each other. So alpha and beta would be, for example, distance 2, but so some gamma over here would be distance 1, 2, 3. You have to go all the way up. And so this might not look super familiar, but the model that we studied, this p-spin model, the states can be exactly put on such a tree. The tree is much simpler, so the tree looks something like this. So these are the states where their overlap is U, and these guys with this have overlap 0. So you can put them on the tree again. And what Dio and Frederick Denef found was that if you study a quantum field, a light quantum field on de Sitter and took some evolution, then the probability distribution of the overlaps in different classical patches also fell on a tree like this. A system like this is called ultrametric. I like that they use ultra because Dio mentioned that they call this metric of metrics superspace, but I think it would deconfuse everybody if they called it ultraspace. And then you would have ultrametric structures on ultraspace. It would be pretty cool. Yeah. And this model had a very simple structure for the overlaps, but other models of glasses also fall in the category where the distances between spaces, between states is ultrametric. And of course, this analysis was for fixed geometry, fixed de Sitter geometry interacting quantum field. It would be interesting to see if this is more generic. For example, if you had you can consider metric fluctuations, if you would see something like this, if the structure would also be ultrametric. But what this signals is that the mode freeze out of a field on a cosmological background tends the system into a glassy phase space, very much like the model that we studied earlier. And this is criminally understudied. I mean, there's very strong evidence to suggest that the type of physics relevant to spin glasses is a good approximation for the physics of the overlaps of these patches. So why not try to study this a little bit more and see if there's any smoking gun signal that we can extract. In fact, this is a case where we could even try to do data analysis on the CMB and see if the structure is present there. Is there some kind of underlying ultrametricity? And it would be a case where potentially these overlaps are much more easier to measure than doing some kind of dynamical correlation and hoping to see something very subtle. So, we're done? We're done.
Questions or not? Ah, okay. Are there questions? Yes.
I think someone else asked, but why can you apply the glass thing to the black hole structure if you don't have all of them equal? Like you have a lot of different charges.
That's a good question. You know, it might be wrong, what I'm saying, that you could apply. It could be wrong. I'm just saying we don't understand that transition.
No, but it's before that. How can you apply if you have in the glass thing you have n copies of something, but in the black hole structure you draw that they are not equal. So they are not copies of the same thing.
Ah, yeah. Yeah, you should maybe think of the black hole sites themselves as the spins rather than the whole system. Like you want your whole space-time is the system. And in one copy you have two black holes, and in another copy you have one black hole. And you want to measure their overlap, something like that.
Confusing, but okay, thank you.
One thing I wanted to ask is that in the beginning, when you were discussing like the physical system that you wanted to describe, there was one important thing was the speed that you freeze, and I don't see like in this spin glass model if it has
In that
an
model there
effect,
was, yeah, that
or here in your cosmological model, because in one I'm in equilibrium and I don't reach the glassy phase.
yeah. So I didn't emphasize this enough. Really, there is. I'm recorded, but I'll say whatever. I'm not an expert, so I'm allowed to say wrong things. I think there are many camps in the condensed matter world, and some people believe that you will never be able to understand the glass transition unless you understand the dynamics of supercooling. And there are other people who believe that you can analyze everything using equilibrium techniques, and you just have to make sure that you find these very subtle signals of the glass transition. And so, you know, there's not agreement that, you know, this is the smoking gun signal of the glass transition. You really have to pick your camp. I represented a model that you can solve only because studying the physics of supercooling and the dynamics of that is not as easy. I know there were a lot of equations, but this is the easiest model of a spin glass you can solve, if you can believe that.
I thought you were going to say that each one of those patches was a different den, like each one of the replicas. But then you I think, said that we want to try to understand the correlation and that.
No. You can think of these as different replicas of the same system. And what you're doing is the universe is preparing for you multiple replicas.
Yeah.
And what you're measuring is the overlap between the replicas.
But I can associate each one of those patches to a number, but a natural number. But you need to take the limit of n going to 0 to do some computation, right?
For this, so long as you can measure all of the overlaps and you can show that they live on a tree, that's probably good enough.
Oh, okay.
We're not computing the log in this example.
Okay, then we thank Tarek again.